I got
I've never seen that shirt on Birkin.
I don't think
Oh, well, it was
I think it's a
the region of Syria that was used to be occupied by ISIS.
Birkin, is that a new shirt?
No, okay.
Never seen it on you.
I haven't seen that.
Yeah, you
When's the last time you bought
I don't think
I don't think we've seen that. No,
I don't think we've seen it.
We haven't
Maybe
seen
it's
that.
the
I think
No,
it's
maybe
the
it's the
top.
top.
I think it's the top.
Well, I mean,
Yeah, the
It's
orange
in the
brings out the
name.
color.
Yeah.
Combo. It's the tie. It is.
The tie brings out your
When's the last time you bought it?
That's just weird.
It's a compliment. Violating man code.
Yeah, that is.
The broker.
Yeah. Yeah, that whole row is kind of in violation.
Because I play soccer right now.
No, no. Okay. All right. Any specific questions on the assignment? Michael?
I have a few.
Okay.
8F.
Well, let's just talk about all of 8. Okay?
Thanks for saying 8F.
So let's just talk about all of number 8.
Let's do it.
Let's talk about that. Let's talk about it.
Let's just jump in.
So here's your graduated cylinder, right? Okay. So you're going to dump in this bar. So right away when you dump in the bar, what's going to happen to the water level inside the cylinder?
It's going to go up.
It's going to go up. By how much is the water level going to go up?
0.05 meters.
Why?
Because that's going to be the exact same.
Yes, because whatever the volume of the bar is however much the volume of the water is going to go up. Okay, there you go. Now, so here's the whole thing. So on number 8, what's the mass of the copper bar? You know, you only have the volume, but what else can you find out about copper?
Density.
The density. And you know, rho, so density of copper is mass divided by volume, right? You can look up the density, you find the, you know, you got the volume, you can find the mass, okay? Not a big deal. So your, because if 8A is wrong, kind of everything else is going to be wrong. So that mass should be around 450 kilograms, okay? It's actually pretty big. So then, what is the copper bar weigh? So help me if you struggle with that question. No. So then you got on D, what is the weight of the water that's displaced? So here's the deal. So remember, your buoyant force is equal to the weight of the fluid that is displaced. So you go FB equals rho VG. So here's the deal. Is this the density of the copper or the density of the water? That's got to be the density of the water because that's what's creating the buoyant force. If it's sitting in air, it would be the density of air. If it was in liquid mercury, it would be the density of liquid mercury. You have the exact same volume, 0.05 cubic meters, okay? And you know what G is, so you can find the buoyant force. So ultimately then, on F, when you get down to that one, okay, what's going to be the tension on the string? So here's the deal. So you've got gravity pulling down. You got your buoyant force acting up. Now, how do you know the buoyant force is less than the gravitational pull?
Still sinks.
It sinks, right? If the buoyant force is bigger, what would happen? It
Float.
would float, okay? It sinks. So you know your gravitational force has to be bigger than your buoyant force. So basically, your tension is going to make up the difference between your buoyant force and gravitational force, okay? So if all goes well on problem number 8, most of your answers on number 8 are going to start with a 4.
Yes.
Are D and E going to be the same? Ish.
Ish. Ish. Okay? That's the whole point of that question. Okay.
Okay.
Okay. Michael?
Okay, 9B.
Let's just talk about all of 9.
Okay.
All right, 10 then.
Yeah, next is 10. Next is all of 10.
Okay, we'll just bank that.
Yeah.
We'll add 10 to the column. Okay. So here's this bar of aluminum and floating in liquid mercury. When something floats, What are the only two forces involved?
FG and FB.
FG and FB, that's it. And what do they have to equal?
Each other.
Each other. So you got your buoyant force acting down, right? And, excuse me, your gravitational force acting down, and your buoyant force acting up. Okay? And those are going to be the same thing. Okay? Start with that basic idea. This is the only way they can float. There's no strings attached. These two forces equal each other. That's it. What do you need to calculate the gravitational force? You need two things.
Mass.
The mass and the gravitational acceleration, right? But do you have the mass of the aluminum bar?
No.
No, nor do you have the volume. So you go, no, Buoyant, you're a jerk. Come on. But knowing the densities, oddly enough, we're dealing with densities. So how could I relate density and volume to the mass of the aluminum bar? Rho VG, right? So my gravitational force acting down is going to be the density of the aluminum times some volume times G. Because density times volume is going to give me mass. Okay, that always gets you mass. So here's the question. This is what we went over yesterday. Is this volume, the entire mass, the entire volume of the aluminum bar, is it the part that's above the water line or the part that's below the water line?
Entire.
Why?
Gotta account for everything.
Yeah, you're trying to find the entire mass of the aluminum bar. So you have to use the entire volume of the aluminum bar. It isn't the part that's submerged, it's the entire thing. Because this isn't going to change whether it's in mercury or not, okay? This is just mg. No matter where you are, this is going to be mg. Yeah, okay, that's kind of cool. Now, buoyant force. What two things do you need to calculate the buoyant force? The density of the fluid and the volume that's displaced, right? So your buoyant force, which this is going to equal, is going to be the density of the fluid. Now, what's the fluid that you're involved in, number 9?
Mercury.
Mercury. Okay? Now, you've got a volume times G. So here's the deal. Which volume do I use? The part that's above, the part that's below, or the entire volume?
Parts that's below.
Yeah, because that's what's creating the buoyant force. So call that volume that's submerged. So right away, what do you do with your G's? You cancel them out. Okay, boom, there you go. Now, think this through. Eventually, you're going to be asked to find a percentage that's submerged, right? Okay? So, do you think your percentage that's submerged is going to be more or less than 100%?
Less.
Yeah, guess what? Because if it was 100% submerged, we wouldn't be having this discussion because the stupid thing would have sunk. Okay? Otherwise known as the Titanic. So, which one is more dense? The density of the aluminum or the density of the mercury?
Mercury.
Mercury. So what do you think I want to put on top? Density of the aluminum or density of the mercury?
Aluminum.
Yeah. So I'm going to have the density. So I'm going to divide this over. Okay? Right? So here's what I've got. My G's are canceled out, so I've got my density of the aluminum divided by the density of my mercury. Now, which is bigger? The entire volume of the aluminum block or the volume that's submerged? Higher volume. Oh, so if I move this over here, that's the volume that's submerged divided by the total volume of the aluminum. Now, at this point, you all were flipping out because you're going, Buoyant, we don't know the volume that's submerged, nor do we know the entire volume of the aluminum block. We can't answer the question. There's an equality here, right?
Oh.
Which means these two numbers are the same.
Equals. That cancels.
Can you find the density of the aluminum?
Yes.
Yes. Can you find the density of the mercury?
Yes.
Boom. There you go. That's it. Right, Olivia?
Yes.
Okay. Yeah. Yeah. Think it through. Now, what do you have left? 10?
10.
Yeah.
Yeah.
So on number 10, here's your water line, here's your still plate. Now, there's two ways that you can work this problem. You can do smash mouth physics, or you can take a more elegant approach. You're going to get the same answer either way. I don't care what you do, okay? So, here's the deal. What do you have in the problem? What are you given? You're only given one number.
Given the mass. You're also
Massive
given,
hole, which is like 18,000.
Yeah.
you're also given the material.
And it's steel, right? So here's the deal. So you're lifting this thing up. So what are the three forces acting on that plate?
Gravity,
Gravity's pulling it down,
tension,
tension's pulling it up,
buoyancy.
and your buoyancy force, right? Okay? So basically, if I add these two values together, that's going to add up to equal what? The weight of the steel. Okay? So this plus this all have to add up to equal to 0. Okay? Now, realistically, if you're doing this, if you get into deep sea salvage, when you're actually lifting this, there's actually like a huge drag coefficient because you're dragging it through water. Okay, but we'll get into that. It's not important. Let's just deal with these. So here's what you've got. So you've got your tension plus your buoyant force has to equal the weight of the plate, right? That's what has to happen. What are you trying to solve for?
Tension.
Tension. So I want to move this over. So I'm going to go minus FB. So the gravitational force, okay, has to be bigger than the buoyancy force. Because if the buoyancy force was bigger, what would happen? Yeah, you wouldn't need the tension. Like, oh, okay, there you go. So, what do you need to calculate the gravitational force? M and G. So this is going to be the mass of the steel times G. Now, if you want to get this number, you can. Okay, if you can just get this number. I don't recommend it, but you can do it. You can do smash mouth physics. Okay, you can do it. You can get the number. But there's a more elegant approach to this. Now, what do you need to get the buoyancy force? Three things.
Mass.
Well, I need density, volume, and G. So this is going to be the density of what? The density of the steel or the density of the water?
Water.
Water, because that's my fluid. Okay? So that's the density of my water. Now I need a volume and then G. This is going to be the volume of what? All of the steel, right? Because that whole thing is below the water line. But here's the problem. Did I give you the volume of the steel? No, didn't do it. Yes, I bark in. Oh, sure, man. But can you find the volume of the steel?
Yes.
Olivia, you emphatically nod your head yes. Why?
Because, the volume equals mass.
Yeah, because, density of the steel, which you can look up, right, is going to equal mass divided by volume. So to get the volume, you're just going to switch places. So here's where the magic happens. Okay, this is why you work with numbers at the end. You try and work with variables as long as you can. So this is going to be the mass of the steel times G minus the density of water. Now, so instead of volume, I'm going to put, in this case, if you solve for this, right? So this is going to be the mass of the steel divided by the density of steel times G. So this is the cool part about this particular problem and how it ultimately plays out. Okay? So here's how this actually plays out. What do you have as a common factor in both of those terms? G and what? Mass of the steel. So you could actually factor that out. Oh, that becomes 1 minus the density of water divided by the density of the steel. And there's your tension. So you don't have to do it this way, but this is why you work with variables as long as you can, because you'll see like these hidden relationships. You go, oh, I can just factor that out. Now, here's the problem. For 12 years, you all have been taught to do smash mouth thinking, and oh, here's a set of numbers, plug it in, and you never see the elegance that exists in equations. Yeah, but here's why this is a disservice. What do you think? What are the odds that you're going to get a job being paid $80,000 a year to sit into a cubicle and crunch numbers all day?
Pretty low.
0. Ain't going to happen. What are they gonna pay you $80,000 to do? Huh? Problem solve. Figure out what the numbers mean. That's what they'll pay you $80,000 to do. Anybody can crunch numbers, okay? You gotta figure out how to work with the numbers. That's what you've gotta get used to. And if you think through problems like this, in a manner like this, that's how you get used to it. It's like, oh, right, hey, look, there's a common term. I can factor that out. Okay, that's cool, right? So basically, if you're on the salvage company and you're trying to do this, what's the only number that you, here's the beauty of this, out of this entire equation, what's the only variable that you're gonna change in the problem? Mass of the steel, right? This whole thing becomes a constant. So what you can do is write a computer program and go, oh, density of water, density of steel, I can get that, multiply that by G. So the only thing that you actually have to plug in on any salvage operation is the mass of the steel. You don't have to work the whole thing again. Oh, solve it. Oh, plug in the mass of the steel, multiply that by that factor, boom, there's going to be the tension in the cable. But you'll never see that if you do the smash mouth physics approach to it. Because you're just going to sit there and crunch numbers again and again and again. But if you do it this way, you go, oh, here's my only variable that will ever change in this problem. Okay? Cool with that? Okay. Anything else? Now, let's talk about, make sure everybody's cool with this. On that question about number 6, what does the air in my room weigh? It's a pretty big number. You should get like something times 10 to the third. Okay?
Number 7.
Huh?
Number 7.
Okay.
That was confusing.
Okay, now let's talk about number 7. So those are basically the dimensions of my table, right? They're half by a 2. And this is a half, right? Okay? Now, think this through. At the end of the day, on number 7, what do you want your answer to be in?
Newtons.
Newtons, right? You want an answer in newtons, okay? So, if you notice, in terms of pressure, well, pressure is force divided by area, right? So right away, what can you find? You can find the area. Oh, okay, I can find that. I get square meters. Okay, so I got square meters. In a physics classroom, what units are you going to use for pressure? Pascals, which is equivalent to?
Newtons per meter squared.
Newtons per square meter. So if you have newtons per square meter, and you also have another number that's in meters squared, how are you going to get rid of the meters squared?
Multiply.
Multiply. So you really don't even have to have the formula. If you can realize, oh, right, pascals, those are newtons per square meter. Oh, I can find the area. Oh, that can give me my force. So force is just going to be pressure times area. But what units is, but in this situation, what units did I give you the pressure in? Atmospheres. Atmospheres. But if you look on your equation sheet in the top left corner, oh, there's a handy-dandy conversion between atmospheres and pressure. So, anyway, so on that one, on number 7, you should, for your force, you should get something times 10 to the 5th. Okay? Now, that's a lot of pressure. So here's the misconception that everybody has. Everybody says, oh, pressure is pushing you down. It is. Okay? I'm not denying that. Pressure is pushing you down. But imagine if there were only 1.01 times 10 to the 5th newtons of force pushing down on the tabletop. If that was the only direction pressure was acting, was down, what would happen to the tables?
It'd break real quick.
Yeah, okay, you could, so all of a sudden you try and lift it up, okay, it's going to push it down. So that's the reason I asked that, is that you have to realize that there's an equal pressure that's on the bottom. Now, that's assuming that it's then technically what creates the buoyant force is a difference in pressure based upon a difference in depth. Okay, that's actually what creates the buoyant force. And so if that was like, if you take that table and you set it up right, technically the pressure on that edge of the table, if you set that table up like this, the pressure on the edge up here is a little bit less than the pressure on the bottom, because there's fewer particles up there. But that's not the point of this story. Anyway, anything else? Now, if you want to hold on to this assignment and hand it in tomorrow with the test, you can. Okay? If you're feeling good about it and you want to get rid of it, go ahead and hand it in. Doesn't make me any difference. So, okay, so the test tomorrow. Now, I want to tell you this right now. There are no retests on this test. It is a one-shot deal. No matter what your score is, that's what you get. Okay? So don't sit there and go, oh, no, don't need to study. I'll just take 3. I'm telling you right now, there is absolutely, in no way, shape, or form, a retest. Okay? So don't even think about it. It's not going to happen. Okay? Whatever score you get is whatever score you get. That's it. Mainly because we just don't have time. Okay? Because then we got to turn around and go take the big fun. So whatever score you get is whatever score you're going to get. Now, to give you some perspective on how complex some of the problems are going to be, like on problem number 2 on your review, we go all the way through O. Okay? So, yeah. So, here's what I'm going to do. We're just going to make sure everybody's on the same page. Here's what a lot of the test is going to be is on pressure volume graphs. Isobaric, isothermal, volumetric. Okay? So we're going to go through all 3 of those. If you got those and you can think your way through that, that's a vast majority of the test. Okay? So let's just start with something simple. So you got a pressure volume graph, and let's say that they're going to have a horizontal line. Okay? So first off, what type of system is it? Isobaric, isovolumetric, isothermal?
Isobaric.
Now, this is what I would do if I were you all. If I had to take this test tomorrow, I'd get like a half sheet of paper, an index card, something, and I would write the 3 systems on it: isovolumetric, and then I'd put it out on one side, and on the other side, I'd write down everything that I knew about those systems. Okay, that's what I would do if I was preparing for this test. Okay, because I always found the more often I wrote stuff down, the better off I was. Just a suggestion, not mandatory, just an idea. Now, so you got a pressure volume going across like this. So, this is going to be isobaric, which means what's going to stay constant?
Pressure
Pressure. But what's happening to the volume?
increases.
It's increasing. So if you want to look at this from the 2nd grade classroom, what are we doing to the classroom?
Making it bigger.
We're making it bigger. But what's happening to the pressure?
There's more Skittles.
No. What's happening to the pressure?
Oh, it's the same.
Stay the same, all right? So you got a room full of Timmies. Are you going to change the number of Timmies in the room? No. Okay, why not? No. What's going to stay the same? No. Why aren't you introducing more Timmies into the room? What stays constant?
Number of moles.
Number of moles. Okay, number of moles is going to stay the same. So, if you're increasing the size of the room, what's the only way that you can maintain the same pressure? Increase the temperature. So what are you going to have to do to Timmy?
Skittle. Sugar.
You got to dump sugar into the system, right? You got to give Skittles to Timmy, okay? Because the only way this is going to happen. Because if you just increase the volume without giving Skittles, what's going to happen to the pressure? Pressure's going to drop because you won't have as many collisions because they're maintaining the same temperature. So if you view the Skittles as being the value of Q, you're going to dump energy into the system. So start with this idea. This is going to be some temperature initial. Okay? I don't know what it is. I don't care what it is. I can find it, okay, but I just don't care at this point. So, when I get over here, is this final temperature going to be bigger or smaller than that initial temperature? Bigger. Okay? So is there going to be a change in temperature? Yes. Is the change in temperature going to be a positive or negative number?
Positive.
It's positive. Oh! So I'm going to have a positive delta T. All right, that's cool. Now, there's certain big equations that you're going to need to have and understand. Delta U equals Q plus W. Delta U also equals 3 halves NR delta T. Work equals negative P delta V. And work equals nRT natural log of VI over dI. Now, this is the only one that's not on your equation sheet, and this is going to be on the front of the test. Okay? So do not memorize this equation. I will give you this equation. It's going to be on the front of the test. You just have to know when to use it. Okay? Now, so here's the deal. I'm going to have a positive delta T. So what's going to happen to delta U?
It'll be
Positive.
Okay? I'm going to have a positive delta U. Okay? Cool. All right? Now, remember, you have to view this between what we can measure and what we cannot measure. Okay? There are no delta U probes. Okay? You cannot measure directly delta U. You can't do it. You have three big things that you can measure with gases: pressure, temperature, and volume. Okay? Those are the big three things that you can measure. Based upon that, we can get an idea of what's happening in the small world, okay, of molecules. Like if, God forbid, let's say that I taught second grade and I was blind. I don't know why, but let's just say that'd be a challenge. Blind second grade teacher. Woo. Okay. But anyway, I say, hey, I need to get a feel for how much energy the kids have. Okay, it's like, so I can stand there and feel like how many times they run into me. Okay, so if they're like bouncing off the walls, right, and go, oh, okay, they're pretty active. They have I'm feeling a lot of pressure because of the fact that I'm having a lot of collisions. Versus, oh, you know, barely I get run into, oh, they don't have a lot of energy today because I'm not feeling a lot of pressure based upon the number of collisions. Okay? So, volume, okay, I can walk around, feel the room, okay, right, got that. And then I can say, oh, hey, Timmy, how much energy do you have? Oh, Mr. B, I'm like loud for sound. It's the day before Christmas, right? So Timmy's like on an 11 on a scale of 1 to 10, okay, right? Or versus, Timmy, how you doing? I don't know, Mr. Camp, I got a fever. Right? Okay, Timmy, you're like at a 1, okay? So I can get a feel for that amount of energy. So you have to realize what we can physically measure in a system. We cannot directly measure delta U. We cannot directly measure Q. But we can do some other things and get clever about this. So remember, delta U is the total energy in the system. Okay, that's what you have to understand. And that's the sum of two things: energy flowing in and the work that you have to do. So if you go with the example of Bree, in terms of what I'm going to leave her upon my passing, what's Q going to represent? How much money I give her, okay? That's the sum total that she's going to get. What's the W going to represent? What she's going to do with it, okay? What she's going to do with it, and delta U is going to be the overall change in her bank account. So I'm going to give her some money, she's going to have to do some work with it, this is how much money is left over.
So that was like energy in the system, energy out, and
Yeah, what do you do with the work, okay? So energy, what you do with the work, you're changing your bank account, okay? So if I just give Bree money and she doesn't have to do anything with it, oh, score, okay? But here's the deal. Here's what's going to be, if you follow this analogy, every story starts with Bree getting some money. So Q is never going to be a non-zero, is never going to be zero. Bree's always going to start with some money. We just got to figure out what she's going to do with it. Okay? So Q is the only variable here that will never be zero. You're always going to have some energy flowing out. You're always or flowing in or flowing out. So Q is the only one of these that will never be zero. Okay. All right. So since I've got a positive delta T, that means I'm going to have a positive delta U. Now, here's the other thing. There are certain things you just have to understand and you have to have straight for tomorrow. What's happening to the volume? Getting bigger or getting smaller?
Getting bigger.
Bigger. So what's happening with this syringe is that I'm here, right? And I'm going to pull this thing back. I'm going to push it back. Something is going to happen to make the volume bigger. So, could I use this equation to calculate the work that's done? Work equals negative P delta V.
Yeah.
Yeah. Do I know my pressure?
Yeah.
Yeah. I don't know my final volume. Yeah, I know my initial volume, right? I don't know the numbers, but I don't care at this point. So I could use work equals negative P. Now, my delta V is going to be V minus V naught. So here's what's important. When I look at V minus V naught, is this a positive number or a negative number?
Positive.
Positive, because my final volume is bigger than my
Initial.
initial. Therefore, work is going to have a
Negative.
negative number. Okay? So anytime it gets bigger, work is always negative. Because because you have to rage against the machine the pressure that's trying to keep it small. So anytime the volume gets bigger, Okay? That costs energy. Okay? You always cost energy. Now, this is also going to be a game of prepositions. So if I say work is done by the system, okay? By the system is code for we got to take some energy and we got to spend it. Okay? So that's like saying Bree has to go spend some money. Work is being done by Bree. That's going to cost her energy. The volume's going to get bigger. Okay? Now, if I say work is done on the system, what's going to happen to the volume? Volume's going to become smaller. That's like compressing a syringe. Okay? I'm going to push this thing together. So you have to know your prepositions. If work is done by the system, volume gets bigger, work is negative. If work is done on the system, volume gets smaller, work is a positive value. Okay? Home run deal. So that's one of the things that you have to know without fail, is the sign of that work, whether it's positive or negative. Okay? Now, here's what's going to happen on the test. In any situation like this, I'm just going to give you numbers. I'm just going to say, hey, you know, a certain amount of work is done by the system and a certain amount of energy flows into it. All I'm going to do is give you numbers. You have to decide if they are positive or negative. Okay? So I'm going to tell you straight up. If it's negative, like if work is, I'm going to say, hey, 500 joules of work is done by the system. I'm not going to make that negative. You have to decide if you're going to make it negative in the calculation of delta U. Okay? So every number, I'm going to tell you straight up, every number that I'm going to give you is going to be a positive number. That doesn't mean that it's positive when you do the calculations. You have to decide if it's going to remain positive or do you make it negative. Okay? So this is all about the prepositions game. By is negative, on, positive. If energy flows into the system, that's a positive cue. That's like me giving Bree money. Bree is spending money, energy is flowing out of the system, Q is going to be a negative value. Okay? So you have to understand the prepositions. Okay. So in this situation, is work being done by the system or on the system?
By.
By. This is it's getting bigger. So now think this through. W is going to be some negative number because work is being done by the system. So what's the sign of Q going to be?
Positive.
Why?
Because you're adding energy.
I've got to add energy into it because there's no way I can end up with a positive delta U and both Q and W are negative. Okay, it can't happen, right? So up here, I know I've got a negative W. So Q has to be a positive number, but what else do you know about Q?
It's bigger
It
than
has to be bigger than W. So in other words, I've got to dump more thermal energy in than the work that I do. Okay? So in other words, I'm going to leave Bree $5,000, but she only has to spend $3,000 of it on work. So she gets to keep $2,000. Okay? So her bank account's still going to go up, just not as much as she's got to keep all $5,000 because she's got to do some work with it. Okay? So Bree will always end up with more money than what she started, but she's got to spend some of it on doing work. So that means that I'm going to have a positive Q that has to be greater than W. That's the only way that's going to happen. So basically, I'm going to dump a lot of energy in. I'm going to use some of it to make the gas bigger, but then I also have to take some of that energy to increase the temperature. Because here's the deal: I can't have all of it go to doing work, because if it all went to do work, then I could never change the temperature. Okay? So Q is what changes temperatures. Volume changes work. Everybody cool with this? Now, in this situation, I can use this equation to calculate that work, as long as I know my initial and my final. Now, what if I reverse the process? If I reverse the process, what's going to happen to all the signs?
this.
Yeah, they're just going to switch, okay? The volume would get smaller, work is going to be done on the system, W would turn positive, Q would be negative, delta U would turn out to be a negative number. So physically what's going to happen here this is what you would see. It's helpful if you can visualize this. Pressure's going to stay the same, volume's going to get bigger. I'm going to dump Skittles into Timmy, but I'm going to make the classroom bigger. Okay? Now, what if I just dumped Skittles into Timmy's, but I didn't increase the volume? What would happen to the internal temperature? It would go really, really big. What would happen to delta U? Oh, that would be really, really big. Because none of that is being used to increase the volume. I'm not doing any work. So it's the teacher's worst nightmare. It's like, man, she's locked into a small classroom and some parent gives everybody a bag full of Skittles on the way in. It's like, oh my God, is that pressure going to go sky high? So there's no way that I can have a constant pressure without allowing that volume to expand. Okay? As long as I'm increasing the temperature. Good with this one. Okay, this is the most complex one. So if you can think your way through this one, which is the most complex one, the other ones will be simpler. All right? So, this isobaric, got this happening, right? So then I can go to the same system, come down here and go, okay, we got some pressure, we got some volume happening here, right? I'm going to start at that same point, but now I'm going to come down like this. Okay? So I'm going to have the same change in volume. So what's happening here? Isothermal, isometric, isobaric.
Isothermal.
How do you know?
Because it's a curve.
Curved line, and there's an inverse relationship between pressure and volume. So if it's isothermal, which it is, okay? If it's isothermal, what is staying constant? Temperature. So if there's no change in temperature, what else is there nothing, what else isn't going to change?
No.
No, not work.
Q.
Huh?
Q.
It's
No,
delta
no,
U.
no.
It's delta U.
Delta U.
Because that's equal to 3 halves.
Okay? Because remember, delta U equals 3 halves NR delta T. So if there's no change in temperature, guess what? There's no change in the internal energy of the system. Okay? So this is going to be 0. So therefore, delta U equals 0. So what's the only way delta U equals 0? Well, Q and
W.
have to be the same value but opposite sign. So the only way this can happen is if Q plus W add up to 0. Now, in this situation, to calculate this value of work, could I use negative P delta V? Matt, could I use work equals negative P delta V to find the work done on an isothermal expansion?
I want to say no.
You would be correct to say no.
Okay.
Why are you correct to say no?
I'm not sure.
Great?
Pressure's changing.
Yeah. This only works when you have a constant pressure. What's happening to the pressure? Pressure's decreasing, right? So, visualize this. What's happening in this second grade classroom?
They're getting less energy.
They're going off their sugar.
Well, actually,
What'd you say?
They're going off their sugar high.
Okay, they're coming off their sugar high. Now, is that correct? Are they actually coming off their sugar high?
No, they have the same energy. It's just that
Why do they have the same energy?
because temperature's staying the same. What's
Temperature's
happening?
staying the same.
Yeah. So the
So
room's
they're
getting,
still on the same sugar high
yeah.
because the temperature hasn't changed.
It's just
Now, Mad Max, what's this?
the room's getting bigger.
Room's getting bigger, right?
So
So by the room getting bigger, what's going to happen to the number of collisions with the walls?
It's gonna go down.
So I'm going to have the same energy with the collisions, but I'm just not going to have as many collisions because the room is getting bigger. So this would be like, imagine that, God forbid, I teach second grade, horrible. Okay? And it's like the day before Thanksgiving, the day of Thanksgiving break. Okay? So all the kids that are, okay, right? I was like, oh my God, too much pressure. I can't really, get the Skittles out of the kid system. That's already there. So what could I do to alleviate my pressure? Move her to, okay, kids, we're going down to the gymnasium today, okay? Mrs. Camp has a raging headache. We're going to go down to the gym, okay? So they're still going to be on the same Skittle high, right? But now we're going to have more room. What's going to happen to my pressure? That's going to go way down, okay? Now, if you want to make my pressure go up, what would you do? Yeah, if you put me in a closet with all these little ankle biters, okay? Oh my God. That would be horrible.
real fast.
Parachute shot. Okay.
Dude, is that the name? Dude, forget the tattoo. Forget the tattoo.
Yeah,
That's
forget
I'll
the
pay money
tattoo.
to do that. I'll
You'll
pay
pay
money
what?
to have you teach a second grade class for one day.
One day.
Yeah, and we'd put you in a closet at
Dude,
the
don't
end.
get rid of the tattoo, man.
Who's paying my lawyer? Because odds are I'm going to get sued, okay, for something. Traumatic influence.
Yeah, just pick them up.
Timmy, come here.
So
And we'll make sure there's a kid named
I'd
Timmy
pay
in the
just to
class.
see him pick up a second grader by the head.
Guess what? If I ever have a kid, guess what I'm not going to name him? Timmy. Okay. Wolfgang maybe. Not Timmy.
Ooh, Wolfgang.
Wolfgang.
Oh my
Oh,
days.
Wolfgang Pauli came up with the Pauli exclusion principle.
Oh, I
Wolfgang
thought you were
Burkamp,
talking about-
come on.
I was thinking Amadeus.
Like,
I
you
was
could
thinking,
party,
I was
you
thinking
could party with a
Mozart.
guy named
would give him
Wolfgang. Okay? Timmy, not so much. Wolfgang, yo! Come
You
on.
think a kid named Wolfgang
Party
would
with a guy
get
named
bullied?
Stan?
I think
No, no, no.
Bully a kid
No.
named Wolfgang.
Okay, no, you cannot party with a guy named Stanley. No, it cannot
Okay.
happen.
Like, Stan the man, of course you can.
Maybe that.
Grade, no
Maybe
one's
that.
bullying
Stan the
him.
man.
Yeah,
Yeah.
Stan the man with the plan.
stand the
Maybe.
animal.
Okay. All right. So,
Your day
so delta U is going to equal 0. So how can I find the work? Can I find the work?
Yes, you can.
Yes, I can.
NRT,
Why?
natural log, because it's a curve.
Because I can do
Let's go, Honus.
work equals NRT,
Natural log.
natural log of VI over
DF.
VF. Now, this is where math comes into play. What's bigger, final or initial?
Final.
Final. So you're going to be taking the natural log of a number less than
1.
1. Now, when you take the natural log of a number less than 1, you get a,
Negative.
which means my work is going to be
Negative.
negative. Okay? Now, I couldn't do this equation if I tried, because my pressure is changing. But could I use this equation if it's a horizontal line? Could I use this to find the work underneath a horizontal line?
No.
Can't do it. Why? Temperature is changing. Okay? So there's two ways to calculate work. You have to know when to use each one. I can't use this on a horizontal line because the temperature is changing. I can't use this on an isothermal expansion because the pressure is changing. So you have to know when to use each one.
So you could just use a general rule. Use this for this. For like isothermal, use W equals nRT, and then okay.
Yeah.
It won't ever change.
Yeah, if you think thermal, think the one that has temperature. Isobaric, think the ones that has pressure.
Okay.
That's the easiest way to think through. Now, so if you look at this, this is something you can measure. Okay, like I would give you the number of moles of gas. I would have to give you the numbers of moles of gas. Okay, you would have to know this number. You can measure temperature, and you can very easily measure the volumes. So the number of moles, that's actually the hardest to measure out of all of this. Temperature is easy. Hey, here's the temperature probe. What's the temperature of the gas? Oh, here's your initial and final volumes. Here's the plunger. Okay, that's tough to look at. Only variable here would be tough would be the number of moles to actually measure that. But after that, it's a home run deal. So after I get my work, so let's say my work is -5, just to make up a number. If my work is -5, what's the value of Q?
5.
5. Because of the fact that they have to be equal and opposite to add up to
0.
0. So on this deal, on an isothermal, assuming that it's an expansion, what's the sign of work going to be? Negative number. Q is going to be a
Positive number.
positive number. Okay? So I got a negative number, got a positive number, boom, we're off to the races. Those are going to add up to
0.
0. Energy going to flow in, energy going to flow out.
If it's expanding, energy is going to flow in.
Yeah, look at Q. You have a positive Q. So here's the question. Would I put the syringe in a water bath or an ice bath? Or a hot water bath or an ice bath? Let's put it that way.
Hot water.
I'm going to dump energy in, but what's that energy going to do?
Increase the volume.
Or increase the volume. So like I cannot have this happening in a sealed system. Okay? So I can't have an isobaric or an isothermal if you have a sealed container. Like a can of pop, you can't do it with a can of pop. Why?
Because that's iso.
Yeah, the volume is locked. Okay, you cannot. This only works when you can change the volume, when you can compress something or allow it to expand. That's the only time you can do this. Okay, so what do we have left? Isometric, right? So that's pretty simple. So here's the pressure volume graph, right? Now think this through. This is me. I'm teaching second grade, God forbid. Okay, I'm teaching second grade, and I've got high blood pressure. Okay, and I can't change the size of the room. What am I going to do with the kids?
Kicking them out.
No.
You got to lower their energy.
I got to lower their energy level, right? Okay, maybe pour some cold water on the little ankle biters. I don't know, right? But I'm going to do something to make them chill out. What?
Just get one of the half Nelson.
No, I can't increase their kinetic energy. Again, they were frowning at me.
Maybe I had a different idea.
So,
Just knock them
on
out.
this slide, why is isometric the simplest of all of them?
Because
What is equal 0?
work.
Work. Why?
Because there's no force, there's no distance to
Yeah,
provide a
there's no
force
change in
over.
volume. There's no area to calculate underneath the line. You couldn't use. Now, think this through. Could you use work equals negative P delta V?
Because there's no change in volume.
Could you use negative P delta V?
Yes.
B would be 0.
It would be
Yeah,
zero.
delta V
zero.
is going to be
There's no change
0.
in volume.
But then you go, oh, maybe it's not. Maybe it's a number. No, I don't know. What pressure would you use?
Well, there's a change in pressure, so
I don't know. Pressure sheet. You can use this if you tried. Okay? Now, could you go, oh, well, Mr. Burkhamp, we got this. NRT, natural log of VI over VF. Okay, that's kind of cool. Okay, Skippy. Volume initial and volume final.
Same.
Same. What's the natural log of 1?
0.
How much work do you do? None. Okay? Could use these if you tried. Okay? If you tried. Okay. So, I'm here, work's going to equal 0. That leaves me with delta U equals Q. So, this is simple. This would be like a sealed system. Like this what y'all did with the test tube. So, I'm going to drop the pressure. I'm going to put it in an ice bath or put it in a hot water bath.
Ice bath.
Why?
Because less movement, less velocity.
Yeah, okay. I'm not changing the volume. I want fewer collisions. Man, it's like, Timmy, Gus, please, go sit down, okay? Chill out. So, if you look at PV equals inert, right? Well, what's happening to your volume? Matt, what's happening to my volume? Don't make this difficult.
nothing is happening.
Nothing
It's
is
staying the
happening.
same.
That's a constant. So to decrease my pressure, what has to happen to my temperature? Decreases. So if I'm going down, I'm going to drop my temperature. So what's going to be the sign of delta U? Positive or negative? Negative, because I'm dropping my temperature, right? My final temperature is going to be less than my initial. So I'm going to have a negative delta U. Guess what? That means I'm going to have a negative delta Q. So is energy going to flow in or is energy going to flow out? Energy is going to flow out. That's it. Okay? So I promise you on the test, here's what's going to happen. It's going to be the problem with most points. You're going to have a pressure volume graph. Okay? Tell you this straight up. And what I'm going to do is I might start it and say, okay, hey, you're here. Maybe have an isometric expansion, okay? Or we're going to warm this thing up to a higher pressure. And then I might say, okay, hey, maybe we'll do a compression to bring it over here, and then maybe do like an isothermal thing, okay? Something like this, all right? So when you get done, you're gonna have some version that's gonna look like this, okay? Or I might go something like this, and then up, okay? I don't know, something, when you get done, it's gonna look something like this. There's gonna be an isothermal, an isobaric, and an isovolumetric, okay? You're gonna have all three on the same graph. And I'm gonna tell you that you come in here and you write down the coordinates of the pressure and volume of each point. So tomorrow, when you get done with this graph, you should look, and I'm going to tell you this in the instructions as well, make sure that you write down the coordinates of the system, okay? Because it's going to make it easier for me to grade, okay? And I'm going to tell you that in the instructions. Part of the points of this is writing down the pressure and volume that correspond with each one of those. Now, here's the beauty of this. You know the pressure and volume. What else could you find at any point?
Temperature.
Yeah, you can always find the temperature. I'm just going to give you the number of moles. It's going to say, oh, the number of moles is 0.1 or whatever it is. Okay? So out of any point along here, you can also find your temperature. Okay? Cool with that. That's going to be big. Your buoyancy, okay, it's going to be a deal like the steel hull, right? Where you're going to lift that up out of there. There's going to be some questions where you're going to calculate like a Q value. Like you might take like ice at -10, warm it up, melt it, and then raise the temperature of the water. So you can think of that as being like a temperature and energy curve. So talked about this. So what's happening on the diagonal sections? What is changing?
Temperature.
Temperature. So your energy is going here to make Timmy move faster. Okay? What's happening on the horizontal lines?
Phase change.
Yeah, this is when you're breaking the bonds that hold the Timmys together. Okay? So if your temperature is changing, use MC delta T. If it's a phase change, it's just mass times that latent heat of vaporization, latent heat of fusion. So when do you use latent heat of fusion versus latent heat of vaporization? Solid is with fusion, boiling is with vaporization. And I promise you, it's going to be something with water, okay, because that's the only data that you have. So tomorrow, you're going to get a constants value sheet with that's been laminated, okay. So you're going to have that same sheet that you all have, okay. So you're used to using it. You just have to know how to use the information. So yeah, that's about it. So here's what you've got. So this is this sheet, and then you've got the answer sheet. So yeah, it's kind of 1 through all the way through O. So yeah.
How many questions are on the test?
I don't even know. It's 20 some. But one of the questions is like parts A through like K or something like that. So, yeah. Okay, we're done. Let me get this handed